In this video, we are going to be looking at two-dimensional polar coordinates. So, if you consider a two-dimensional system where you have x-axis and y-axis, and say you have a point P, that point P will have some value of x and some value of y. And this value of x and this value of y combined define the position of that point in space. However, we can use a different coordinate system. So this coordinate system is called Cartesian coordinates, Cartesian or rectangular coordinates. You have x and you have y. But what if I want to use instead the distance between the origin and the point, let's call that r, and the angle that this line makes with the x-axis theta. We call this system of coordinates polar coordinates. And it turns out that this coordinate system is quite useful in a lot of problems. We can use very simple trigonometry to see that x equals to r cos theta and y equals to r sin theta. Similarly, to go the other way from xy to r theta, r would be x squared plus y squared and square root of that. And to get theta, note that tangent of theta is opposite y divided by adjacent x. So theta is simply the inverse tangent or the arctangent of the ratio of y and x. So now we can go from xy to r theta or r theta to xy. But what I essentially want to do is, in order to in mechanics, we have to look at forces. If you're doing Newtonian mechanics, and the Cartesian coordinate way of looking at forces is that we have a component of force in the x direction, and you have the x unit vector plus the component of force in y direction and the y unit vector. But say I want the component of force in the r direction and the radial unit vector and the component of the force in the uh, angular component of the force and some unit vector corresponding to theta. Say I want this. So how do we proceed? Well, I note that force is simply mass times acceleration, and acceleration is the derivative of velocity with respect to time. And of course, velocity is simply the derivative of position r with respect to time. So if we if I want to write vector r, which is the vector from the origin to the point P, so this vector would be vector r. It would have a magnitude of r, which is of course this length, and unit vector r, which would be in this direction. So r would be in this direction, whereas theta would be perpendicular to it in this direction. Since it's coming like this, so this would be theta. So these are our unit vectors. But here, if I want to get force, I want to get the derivative of r unit vector. And it is not immediately clear whether the derivative of the unit vector would be a constant. Perhaps this actually gives us something non-trivial. So in order to study this, in order to look at this more carefully, let us say that at time t1, vector r has position 1, and at time t2, vector r has position 2, right? So let's say that this is r1, and at a later time this is r2, and let's call this small angle delta theta. So this is the change in the angle of the of our uh, position vector, and the change in the position vector or the radius vector is delta r, right? And you can sort of notice that this change is in the theta cap direction. So by looking at this, we can say that delta r, or r2 minus r1, which is delta r, is, so if you remember s equals to r theta, this is simply r, and which is the magnitude of both r1 and r2 is approximately r. You have delta theta. For infinitesimal theta, this r would be the same. We have delta theta, which can be arbitrarily small, and this changes in the theta direction. If I divide this r vector r divided by r, I get delta r unit vector equals to delta theta theta cap. I can divide it by t2 minus t1 or delta t and take the limit as t1 approaches t2, and I would get the time derivative of the unit vector r equals to theta dot theta cap. So when I actually perform this entire calculation to get the force, it will turn out that I not only do I need the time derivative of the position unit vector, or of the radial unit vector, but I would also need the time derivative of the angular unit vector, theta cap. So let me just perform that calculation right now, because I would need to do it anyways. So let's say this is R1 again, and this is again R2, right? So so here theta would be in this direction. I'm calling this theta1 vector, which has the magnitude of theta1, and the angle and the direction is theta1 cap, and this is theta2. So looking at this, I can see that if this is theta1 and this is theta2, oh, these are both vectors, and here again the change is delta theta. The change in the angle here again is delta theta. And what do I want? I want this. I want delta theta vector. Similarly, delta theta vector would be from s equals to r theta, the magnitude of this for very small changes in the angle would be theta. Uh, would be theta. And s equals to r theta. So magnitude is theta, and this angle is delta theta. And notice that this change uh, is perpendicular to the theta, so it is actually going this way rather than that way. So it's in the negative r direction. I can divide this here and get delta theta cap equals to delta theta. Just take the negative outside and get r cap, and divided by delta t and take the limit as t1 approaches t2, you get theta cap dot equals to minus theta dot r cap. Okay, so now we have the time derivatives of the r and theta, the polar unit vectors, and we can now perform a desired calculation. Let us just take it step by step, and first see what the velocity would be. V would be the r dot vector, so we have the time derivative of r cap, we have to perform the product rule. First we have r dot r cap, and then r stays same, and we have the time derivative at on the r cap, r hat. And if you go above, you see that what is our time derivative of r hat? It's theta dot theta cap. Okay, so we have r dot r hat plus r theta dot theta hat. Okay, and theta dot is essentially um, theta dot is essentially uh, omega. We call this omega. It is the angular velocity, the angular speed. So we see that the radial component of the velocity or the radial speed is simply r dot, which is, this should be expected, of course. But v theta, the angular component of the speed, is r theta dot or r omega. And depending on your background in mechanics, this would be expected as well. This is just the angular speed. Okay, so having gotten velocity in polar coordinates, we can go on to acceleration. So we take the derivative of the velocity of this. Here we perform product rule again, r double dot r cap plus r dot dr cap dt, plus here product rule again, but there will be three terms instead of two. So r dot theta cap plus r theta double dot theta cap plus r theta dot d theta cap dt. So now we can plug in the values. You can go up and check. This was theta dot theta cap. I'll just write the rest as they are until the last term. And here d theta dt, let's just go back and check where it was. It's minus theta dot r unit vector. So minus theta dot, there was already a theta dot, so this would become square r unit vector. Let us just combine the terms. So for the r unit vector terms are r double dot minus r theta dot square. As for the theta cap terms, so this term and this term, these are the same. So let me just write this one first, r theta double dot plus 2r dot theta dot. Okay, so we have the acceleration, and remember that theta dot is angular speed, omega. Similarly, theta double dot is sometimes written as alpha or angular acceleration. So this term which is additional to what we would usually expect in the radial direction, is referred to as centripetal acceleration, which you've probably seen in your previous studies in physics. And here as well, this would probably be expected in the angular direction. This one, which is the additional term, is called the Coriolis acceleration. So we can now finally write that the radial force is mass times r double dot minus r theta dot square, or the angular velocity square, angular speed square, and the angular force is m r theta double dot, or the angular acceleration alpha, plus 2 r dot theta dot, and there you have it.